All right, welcome to my talk of day 2. My name is Joshua. I'm going to be talking about reasoning and specifically how we've made reasoning and an actor computational model play really nicely together to produce a much more scalable and a completely brand new rewritten reasoning engine for the 2.0 TypeDB release. We've had some really good talks over the last 2 days. It's getting towards the end of day 2, and it's my privilege to talk to you and close out some of these sessions today. And as we do that, I'd like to get into more the deep details and the deep internals of how TypeDB 2.0 works. And that's kind of the key question that we're going to be talking about, the how. We had some talks about what can you do with TypeDB. There was some great applications level stuff. We had some of the more philosophical questions about the whys, like why would we rebrand? Why would we use TypeDB? Why type systems in general in the keynotes and the advantages of doing that. We're going to switch tack a little bit and talk way more about how. So what we're going to do is we're going to talk about this particular question. We're going to talk about how actors enable an engine, a reasoning engine that is scalable and very nice and elegant to think about and talk about. Now, there's 3 parts of this question, right? There's actors. We need to know what an actor is to answer this question. There's a reasoning engine, so we're going to have to do a little bit of exploring what reasoning is and how it works. And then the marriage up of the two, right? So how does an actor and a reasoning engine cooperate? How do they come together to produce something that is actually good? And so just to get started on this, we'll have to start with actors because that's kind of the foundation at this point. So let's jump in. So what's an actor? Well, if you've never heard of an actor is a computational model. And in this computational model, we represent our computational world, which does some work for us, as a set of actors. And each actor lives independently in this world and can receive messages via its message queue, which is sometimes known as a mailbox. And based on those messages it receives, it can do one of 3 things. Now, the actors will always process their messages that they get, which represent work to do or some signal in the system, one by one. And then they can choose to either spawn more actors, which is how you expand this computation scope that you can do at any given point. You can do something internal within the actor, so you could decide to count, or you could decide to log something, or lastly, you could send further messages. And this propagation of messages, but when you receive a message and send more messages, is how actors can collaborate, even though they're technically completely independent in the world, to do useful work. And so there's key ideas here. There's also 3 key ideas. The first key idea is that each actor is single-threaded. And this is kind of the byproduct of this kind of consuming messages one by one approach. We'll get back to these again in a second, but the second idea, as I've been talking about it here, is that these actors live completely independently in our world, in our computational world. And as a result, they can know nothing about each other except that they can exist and that they can send them messages, maybe of a certain type. But the internals and how an actor does its work is completely hidden. There's no way to access it, and if you do, you're probably likely to break your system. And we'll be able to see in a second that if we combine these 2 assumptions, we can achieve very scalable and very simply concurrent systems without the particular nasties that programmers of lower-level libraries, especially like C, will be familiar with, that we don't like to think about and can be very buggy, such as locks and synchronization primitives of other kinds. Now, to think about these bits one by one again, we should just visit what an actor actually looks like. So conceptually, they're very simple, right? So an actor is something that can run a message. You can receive a message and operate on it. And you might have some way of receiving multiple types of messages. So here we have an A and a B message. And to complement an actor, we have something called an executor. Now, an executor might look like an event loop or something that is a single thread that essentially just goes around in circles and looks at the queue that the actors have and takes the messages one at a time. It'll take that message, give it to the actor, say, hey, run this on my executor, and therefore the work gets done. And when it's done processing a message, it'll take the next message on and on and on and on until there's no more messages, and it goes to sleep. Now, because an executor is a single thread that spins around and consumes the messages, all actors have to be single-threaded. And the thing I've missed out here so far is that an actor can only be assigned to a single executor. Now, the converse isn't necessarily true. You can have multiple actors living on one executor. This is still fine. It doesn't violate the assumption that an actor only runs on one thread at a time. But it just means that the executor will be doing one bit of work in the first actor, then the second actor, and the third actor, depending on the messages that it's delegating to these actors to do at any given point in time. Now, this also works because these actors are completely independent. They share no internal state. You can't have any global data structures if you're doing this completely properly. And therefore, they can only communicate with each other, even within the same executor, by sending messages. Now, this even extends to sending themselves messages, right? So if an actor wants to delegate some work to itself in the future, it can send itself a message, which will then asynchronously be executed once the message gets to the top of the queue and the executor processes it. But what happens if you have these three actors here and they're processing messages, but no matter how fast the executors can go, it's got a limited speed, right? How fast it can process messages. And maybe messages, once they're accepted by an actor, are very, very computationally heavy in what they're doing or what they're indicating the actor should do, and the queue just backs up. Well, simply what we do is we create more executors, and then we decide to assign the actors to different executors. And now this is as concurrent as the system can get, as optimal as it can get. Every actor lives on its own thread, essentially, and will run messages designated for it via its queue as fast as it can. And to not use up computational resource when it's not doing anything, the executors simply go to sleep when the queue is empty and wake up as soon as there's at least one message. And very simply, this is how an actor model works. You have actors, you have executors, and you have messages, and your interfaces for communicating and collaborating on work is just a message. Now, to do a very quick example, let's say you're a bank, you have payment processors in different parts of the world, in different continents. They're processing transactions, which we've here represented as messages. The payment processors themselves are actors that live on their own executors. And as they're processing these messages, they'll do some work internally. And now someone from the business department comes along and says, hey, yeah, you know what, it's great we have these independent continents, but we want to know what's going on globally. And we'd like to see how much money is going in and out of the bank at any given point in time. So what you might do then is you might add another actor, right, to count. And essentially you're going to have some total tracker that receives messages and essentially merges messages into the single queue here from all of these payment processors. Now, what's just missing is maybe another dashboard or something which we'll add, which we can represent as another actor to receive periodic updates about the current status of the bank every so often with a time, and then the business department can kind of basically plot this or decide to take some action. Maybe if they're losing money too quickly, they'll decide to shut down the bank for the day. And this is practically how actors work. It's really quite simple. It's a very nice computational abstraction we can make, as well as using it as a computational model. If we can find a way to think about our domain as these independent workers that have a interface we can cleanly define via these messages that we send. All right, so where can we find actors? Well, we can find them actually all over the place. One place you might have picked up a hint on yesterday is in Ganesh's talk about TypeDB cluster. And the TypeDB cluster system runs on the Raft replication protocol, and the replication protocol itself runs on, guess what? An actor system, using the same library actually as we use inside TypeDB core. Now, other places you might find an actorish library is in Spark, and in general, most large-scale data processing libraries, and especially graph processing libraries. Most languages You can find some application that has used actor models. You'll even find libraries prepared by other people in most libraries. And I'd like to encourage you at this point to think about your own problems that you're working with and think about, maybe I can model this as an actor and not only benefit the scalability and the concurrency benefits, but also just to have a mental tweak, because it does lead to very clean abstractions that have to be designed via these messages that can be passed around. Great. And I like to summarize this as this tagline: work smarter, not harder. And this applies when you have such a domain that you can abstract away into these independent workers in your computational domain. The not harder bit references the idea that we don't need to do more complicated stuff. We can be simpler, no locks, no global blocking, no synchronization, none of that stuff to achieve concurrency when we can think in this way. So, back to this question then, how do actors enable an elegant and scalable reasoning engine? Well, we've covered actors, so the next sensible thing then is the reasoning engine. And at this point, if this is you, I would say you're in the wrong talk, but I'm the only track. So let's just do what I would normally do, which is say, go read the docs. But I don't think that's actually such a good idea today. One of the reasons being that I think my mum's in the audience and she probably will not actually go and read the docs. So I think what we should do actually is go and do an example of what reasoning is. Now, what is reasoning? Well, reasoning, we're a database. Reasoning is an alternative way of finding answers to your queries. So in a simple example here, let's say we are trying to find dual citizens in our database, and we have some world in which we have people, and people are related to parents, and people are also born in countries, and those countries have names, and the people have names. And you want to find a person whose name might be John, who has two citizenships that are different. Now, notice on the data that I've represented on the right-hand side, we actually have no information about citizenships. But maybe we can derive some information about citizenships. And this derivation, this inference of how do you find information based on existing information, we can do with a rule. Now in TypeDB, there's a couple types of rules you can write. This is the basic form where you infer a relation. And this rule basically says when you have a born-in relation, so that's the syntax we should hopefully be familiar with by now after the conference, we have a born-in relation with the brackets that says when you have a variable representing a person P and a variable representing a country C, when this person has a relationship to a birthplace C, then we can actually infer that that person has actually got a citizenship to that country. Now, what does that look like in the data? It looks like this. First of all, we can find that there is this citizenship based on the person and their country built by the fact that we have a born-in relationship. So we'll find here that this person called John has in fact got a citizenship in the USA. Now, we can additionally find something else, and that is that the other person in our system that we know about, which is Amy, has a citizenship in the UK based on the fact she's born in the UK. So that's all well and good. We've now inferred two new pieces of information based on existing information we had. What else can we do? Well, we might look at our world model in our domain and our schema and decide actually we can write one more rule. And that rule says actually you can inherit citizenships. And when you inherit a citizenship, it basically says when you're a child of a parent and that parent themselves has a citizenship, then that child can also have that citizenship. Now, in our data on the right-hand side, we have exactly one pattern that looks like this, which is that the person John has a parent, Amy, and that person Amy, we've already inferred via the other rule, so this is a chained inference essentially. The other rule has told us that Amy has a citizenship in the UK. And combining these two pieces of information, the rule tells us when those are true. We can actually also assert that it's true that the child, John, has a citizenship in the UK. And now, based on these two rules, we've derived three new pieces of information about citizenship, notably one answer to our original query, which is that John has two citizenships that are different, the USA and the UK. And that would be the answer we expect to find to our original query about John's citizenships. Now, how would a computer do this? Because as a human, when you're looking at a visual representation of the data, it's really easy to do these kind of ABC steps, so if this, then that. And the computer has to be able to do this as well. And that's essentially what a reasoning engine does. And that's specifically what our reasoning engine does as well. Now, we take advantage heavily of having a strong type system defined by the schema that applies to all the data. So we have a closed world domain, essentially. And based on this information, the rules, the data, and the schema, we can actually automate all of the reasoning. What would a computer do if we were just kind of trying to implement it? Well, we might start by wrapping the query in some object that we're going to call a conjunction. And a conjunction is a good name for what it means. A conjunction means a set of things that all together must be true. And we have several parts, right? We are looking for a person, John. We're looking for a citizenship of John, C1, and another citizenship of John, C2. And we also want to assert that they're different. Now, what can we do to answer this? Well, there's no data in the database, as I showed you, before the rules are run, that actually tells us anything about citizenship. So if we were to try to execute this query without a reasoning engine, we would find nothing. And what we might do to try to remedy that is we might try to, first of all, reduce the problem space. We'll take out part of the subquery and put it up here. And now we'll look at this query more closely, and we'll realize that, hang on, this interesting bit, the citizenship, is something that can be inferred. It can be deduced by a rule that we've written, as we saw. And what we might do is we might apply this rule. And what I mean by that, what we might try to do is we might try to write the rule together with the query we started from, and we end up now in a state, if we use the inherited citizenship rule, that says, yeah, I'm looking for actually a child called John now that has a parent, and that parent has a citizenship. And if we can answer this, we can actually answer the previous state we were in, the previous query, the subconjunction. Now, maybe at this point, we'll do some work to find that this $child is actually the data point John that I'm going to represent here with just caps John to show that we found some data point that we're going to substitute in here. At this point, we can actually define what we're doing. So this is the quick resolution algorithm. This is how a query gets answered using reasoning. And essentially what you do is you repeat this process over and over again of splitting a bigger query up into subqueries and applying rules. And you do this over and over again until you get to a point where there's nothing you can do except look up data in the database that actually exists. So let's apply this a few more times. Well, there's one more thing in here that we can split out, which is the citizenship. And we take that out into its own little subquery. This has an applicable rule, and let's say we apply this time the other rule to find a citizenship which is based on the birth of a person. Now, in this case, we can actually find an answer. We can find that, let's say, Amy is born in the UK. Once we do that, and we look this up in the database, this thing at the top of the stack here that we built a stack of places we've been. We're currently at the top of the stack. We've answered every variable that there is. There are no more unknowns. All we can do is return the answer back down. And that's exactly what we'll do. We'll push Amy and the UK back down into the place we came from. And we'll do that again here because there are no more unknowns in this subconjunction. Now, when we do this, we're saying that Amy has a UK citizenship, right? So this was already inferred by a rule based on some birth, but we don't care how we got there anymore. We just care about the fact that Amy has a UK citizenship. When we do this, we can push us back down again, and we can say, hey, look, now we know what all the variables are in this merged rule and subconjunction. Now we know that, hey, John has a parent, Amy, and Amy has a citizenship in the UK. And when we backtrack again and we propagate this answer to the place we came from, and going back down the stack here, we'll actually be able to deduce that John has a citizenship in the UK. Now, again, we don't care how we got here, right? We know that we have some true path to get here from the stack that we've now removed. And some rules were applied, we created some new information, and we're at this point now that John has a UK citizenship, which we didn't know when we started this process. And if we just push this down again one more time, we've fully filled in C1 and $P to know that we have 2 answered variables and we're down to 1 missing variable we know nothing about. And if we were to continue this, we would essentially repeat building up the stack here, looking for C2, and hopefully come all the way back down to evaluate the not bit, and then find an answer that is valid. We're not going to do that now. We'll do a bigger, more complete example in the new model of how this works towards more the end of the presentation. Now, I think what we're going to talk about, so essentially what this is a stack-based execution model. And this is actually a lot like how we executed queries in 1.x, actually all the way going back. And what you end up doing is you end up merging queries with rules, and you end up with new queries, and you put these on a computation stack as a new state, and you build the stack up and down till you find all the answers, and then eventually your stack shrinks down to 0, telling you found an answer to the original query. Now, one of the problems with the stack is, although the implementation might look okay, it is inherently single-threaded. Stacks are not simple to parallelize and would require locks. If multiple workers were trying to be adding stuff on top of the stack, well, you would need some kind of branching stack, which adds a kind of complexity we don't really want to be thinking about. Now, another thing, all of this means that the algorithm itself, the resolution algorithm that we've implemented with the stack, isn't scalable. So we can't give it more computational resource and expect it to work any faster. It's strictly stuck in one computational core on your computer. Now, one thing that I haven't really touched on yet, but we're going to get a lot more into, is the ability to reuse work. And what I mean by that is, if we were to continue the previous example, we'd actually find that we come back to the same state twice. And identifying this in a stack-based model isn't as easy as you would like, and then notably it gets even harder to reuse the work we've already done. Lastly, the model that we just went through is a bit difficult to convey. It's a bit difficult to explain the resolution algorithm, and here at Vertical we don't really like things that are anywhere obfuscated or hard to understand, because not only does it mean it's harder to bring people up to speed when you're making changes or maintaining things, it is your own mental overhead you're paying that you have to cope with. And if you can lower that activation threshold, you yourself can work faster. And so how do we remedy this? Well, what we like to do is starting with clear vocabulary. And what we do is, looking at this domain here, is we're going to try to find some better terms for what happens. And in the first case, we'll start with the conjunction. We like the term conjunction, actually, because it very succinctly captures what this piece of state, this piece of data means, right? It's a set of things that must all be true to answer the query. So let's stick with that and not change it. But let's look at this first bit. Let's say we were to split out the first line of the conjunction. Well, what do we see here? We see actually nothing interesting at all. We see that P is a person that has the name John, right? That's pretty trivial. We know there's a John in the database. We've seen the data. And, well, all we can do really is look this up and hope there's some data. There may not be. We know there is in this case, but there may not be. And the fact is that it's not interesting is because there are no rules applicable to it. Now, something we know that have no rules applicable to them, well, we're going to call this a retrievable. And a retrievable is something that you can only retrieve and nothing else. You might not find any answers, but it's a retrievable. You might not succeed. Which is a good name exactly for what this does. Now, the next bit is interesting, isn't it? So a citizenship can be concluded from 2 different rules, actually. And what we're going to do is we're going to need a term that encompasses the fact you could look this up, maybe it'll fail, or you can do something from a rule to get this answer. And eventually we ended up on Dan's favorite word of the month for several months running, actually. We're happy to say it's such a cute word. It's the word concludable. Now, what this means is you can conclude this piece of information, this fact, from at least one rule. If we were to proceed here, the next bit is actually also a concludable because it's exactly the same pattern with just different names. And lastly, this bit we're just going to call a negated because something that's not true is negated. And what we're left with is the rules that we have to apply. The word rule, self-explanatory. If you've used our database long enough, it's such a common standard term that we didn't really feel the need to change it because it's very meaningful to us and our users, and everyone can understand that. There's nothing complex about it. And what we end up with here is a term that encompasses all of these, right? So these are all types of resolvables, our data structures we use to build a resolution algorithm. And there's a nice symmetry here that's saying all of these things you can try to resolve in the process of resolution to find an answer. And so we really like this terminology. It helps us explain what we're doing to each other as well. So I think that's probably enough on a basic reasoning engine. You could implement a reasoner like this. We have done it. That's what the previous version did. And we're trying to move along to something that is more scalable, that can take advantage of more computational resource and hopefully do some other tricks to get a bit faster. So we're going to talk about the combination of actors and reasoning now, because that's the ultimate question here, right? How do we end up with a nice, simple, elegant, and scalable system when we use actors? So we'll introduce the two. We'll introduce resolvables, our reasoning building blocks, and actors. And what we get, actually, we call the resolvers. Now, this is a cute name as well, but keep in mind that it fits very, very well with what we're trying to do. We're trying to have some worker, an actor in this case, a resolver, that handles the algorithm for resolution. And it does that by operating over resolvables. So we have a nice triangular bit of terminology here that all interact together and together convey very succinctly exactly what's going on. So the resolver family, we've merged these guys now. They got along like a house on fire, and we're gonna introduce the resolvers. Now the first one is just a conjunction resolver. We're just gonna wrap the conjunction in a resolver and call that a conjunction resolver. The next thing, actually, we're gonna do something pretty similar, which is wrap a retrievable in a retrievable resolver, which can do some work to look up data in the database. Now, the next bit, funny enough, happens to be a concludable resolver, just like the one after that. But keep in mind, we're now in an actor system. All of these resolvers are going to be running on some event loop, some executor, and going to have to collaborate to do work. Now, what we don't want is to create like an unbounded number of actors. We don't want to keep creating new actors all the time. We'd like to reuse them where we can. And what we found is that actually we can constrain our system in a way that these concludables are completely reusable and identifiable for reuse. How do we do that? Well, what I just showed you is that we've merged two concludable resolvers that actually contain the same structure. And what I mean by the same structure, they're trying to infer the same type, the same citizenship, they're looking for it at least, and between two things, a citizen and a country. All that's different between these two concludables is the variable names. And the variable names actually don't matter at all. As we're processing, we can compute remappings between them as we need, and unmap and remap as we travel through this messaging system without too much overhead at all. So we'll merge them. And we can just give them some arbitrary names, A and B, because it doesn't matter at all. And lastly, we have the negated resolver. Funny enough, we just tagged on resolver there to make it mean something to us in our domain. And finally, we have rule resolver for each of the rules that we're going to keep. And that's the family of resolvers that we're going to need for this example. There are more. If you look in our code base, you'll find things like explanation resolver, disjunction resolver. Rule actually has two different types. But fundamentally, this is the process we need to go through to implement the basic conjunction resolution that we need to explain. So let's do that. Let's do that now. Let's go through the exact same example end to end from the beginning. Now, in the beginning, we had this person with a conjunction. In the conjunction, we're looking for a person, John, with two citizenships that are different. I've put this little executor loop here with the Q because let's not forget, these are all actors now. They're no longer on a stack. They're no longer just conjunction, retrievable, concludable. They're resolvers, which are actors, and live on an executor with queues. They still communicate by messaging. And in this example, we're not going to keep this queuing system visible. We're just going to keep it in the back of our mind and simplify the diagram. So on with it. So what does a conjunction resolver do? Well, it'll analyze its query and split it up. Similarly, as before, which is the core of the resolution algorithm actually, and pull out the first line, which we know is a retrievable. Now, one of the actions a resolver can do is it can spawn new child actors. And what we call a child, actually we like to call downstream, because they are downstream in the flow of messages, and then the caller is the upstream. And so what we do is we take this first bit and we send a request that we have defined in some way to the retrievable after we spawn it, saying, hey, you know what, find me an answer because I'm interested in what P is. And this retrievable will go away and do some work. In this case, it's a retrievable, so it'll try to retrieve an answer, and it'll come back with P is John, just like in the stack example we went through. And the conjunction will say, great, got that, understood, next piece. And the next piece is going to end up spawning a concludable resolver for this generalized generic citizenship relation. Now, we already know that A is John from the previous retrievable, so we're going to carry that information along. As we do this, the concludable will take this message in and decide, well, there's no data I can find that matches citizenships for John. Nothing has been created. There doesn't exist anything that the user has given me. So what I'm going to do is I'm going to delegate work to a random rule that I can apply to inherited citizenship. And this rule will say, yeah, okay, I'm going to pass this on to the conjunction I contain as the when of my rule, which contains two parts. So inherited citizenship, remember, depends on a child having a parent and the parent having a citizenship themselves. And in this case, we actually already know the child is this instance John, and the conjunction resolver that's below the rule, downstream of the rule, will go away and spawn a retrievable for the first part here. Now, a parentship doesn't have any applicable rules, so it is a retrievable. And that's basically how we switch between retrievable and concludable downstreams. It's simply whether we can find any applicable rules. Now, the retrievable will come back saying, yeah, look, John has a parent, Amy, and now the conjunction knows that parent is Amy. And based on this, we'll actually continue and try to answer this citizenship. But notice, the citizenship that we're looking at here has exactly the same shape, again, as the conjunction at the very top, the entry query that the user wrote. And based on what I've told you, that our actor model is we want to reuse actors where possible. And in this case, we will. We will actually reuse this concludable resolver, knowing this time that we want to find a citizenship for Amy rather than John. The concludable will do something internally, and maybe it'll decide to visit the other rule to answer this question, what citizenships does Amy have? The reason we do that is because we like to circulate the rules we trigger so that when this entire thing is actually flooding with messages concurrently, we balance the work between the rules as best as possible. Now, this rule will go through and try to derive a citizenship for Amy, who we know is born in the UK, which will lead to a UK citizenship for Amy. The rule resolver will insert this fact into the database for use later if we want it. And we come back to the conjunction resolver on the bottom left. Great, we've answered this entire conjunction. We can go back up to the rule, say, yeah, great, John has a UK citizenship based on some information we had before, but ultimately because they have a parent, Amy, who has a derived citizenship in the UK. Come back up, every variable here is answered, and we go back to the big conjunction at the top. And essentially this process can repeat for the next citizenship. Now, something interesting is about to happen, which is we're going to send the request, hey, John, to the same concludable we did before. And if you have a really sharp mind and you were really paying attention, you might have noticed that we sent this request already, earlier, at the very beginning. Now, this is a benefit of using actors and implementing resolution, the resolution algorithm, as an actor model. The fact that we get the same request twice is this work reuse property we were hoping to get in the beginning. And in this case, the concludable, completely transparently to all of the other actors, because remember, they're completely independent, they share nothing. The concludable will actually be able to resume the search it did for answers when A is John. Now, it can do this from all kinds of different places. We can actually share concludables across queries in the transaction. We can do all kinds of fun stuff. And this can lead to a lot of reuse of work and reuse of exploration we've already done in your data to find information. So let's pick up where the previous request left off. And remember, the previous John request went down to the inherited citizenship. And in this case, we already know that's been computed. So let's go to the birthplace citizenship. Birthplace citizenship actually tells us John is born in the USA. We end up inferring a USA citizenship for John, and we come back to the top. Now, all that remains at this point is to verify that, in fact, the USA and the UK are not the same, which I believe they're not anymore. So we will check that in the negated resolver, which will come back true, and we're done. So we have an answer at this point to every part of this query, and the conjunction can finish, right? It's done. It's found John has two citizenships, the UK and the USA. Now, in the Reels model, we're tracing the request flow of one request through the entire actor system, the resolvers, to find one answer. What can happen in the actual implementation is when we enable concurrency, is we can send a batch of, say, 50 requests at once to the conjunction, which will process them one by one, send them off to the retrievable, and now, as soon as the first messages end up in the retrievable, the conjunction and the retrievable are processing at the same time, retrievable will respond, and then as the processing expands, all of the actors will be processing some of these 50 messages. And that's essentially how you can achieve concurrency in an actor model. You can, at least in our implementation of resolution, we achieve concurrency by just sending more messages. And that's a very simple way of achieving concurrency compared to, say, locking and all this nasty stuff that we don't like. So in this case, actually drawing this out in PowerPoint is a bit of a pain. So what if actors, think for a sec, actors, they have a well-defined identity and they know who they're sending messages to because they have to know that to deliver messages. So why can't we just make the computer draw these diagrams for us? And this turns out to be incredibly easy. We created that in like an hour or two, and it's been one of our most useful tools in debugging the reasoning engine and observing the behavior. Now, so actors and resolvers even plot themselves nicely. So many nice properties coming out here. And what we find is this diagram that's been generated by the computer for this exact query that we're looking at looks incredibly similar. We have a conjunction at the top, a retrievable below it, downstream on the first left-hand side. Then it goes to a concludable, which has two applicable rules. And at the very end, on the right-hand side, we have a negation. Now, what this is it visits two rules. The whole system propagates 37 messages to find one answer, and it takes about a millisecond, actually very much less than that, closer to 100th of a millisecond to find our answer that we're looking for. So this is a very simple, trivial example. Basically, what happens if we throw some more complexity at it, right? It's kind of what we want to know. Does it scale? So in our internal classical automation system, in our internal CI, we have a permission system on the website built in that runs on TypeDB and has a rather extensive set of permission rules. And normally you look for like, is this user allowed to view this page, blah, blah, blah. But just to make it really hard for the system, we're going to ask for all users with all of their permissions and all combinations. And this will be quite heavy on the reasoning. And what we find is it looks a bit more like, is it going to render? Okay, it does render. It looks more like this. I was worried about the image size for a sec. So this is even a medium-sized example, I would say. It visits 12 rules, the system sends 631 messages, and the whole thing takes 21 milliseconds to find an answer. And in this diagram, so I forgot to explain, the blue is a request, similar to our previous diagram, and the green is an answer that the resolver finds, and the red is a failure. So sometimes you fail to find an answer, and you notify your upstream, and it can take some more action. So that's quite cool. It's actually very easy based on the diagrams here to see where maybe excess work is being done. Maybe we need to spend some time digging down there on the bottom right to see what's happening. And in general, this has been very fruitful in finding optimizations combined with the actor model itself, which reveals optimizations almost naturally in terms of caching and reuse of work across queries and within one query. Now, a lot of talk about actors. They do scale, and our implementation does improve with more CPU resource. It's just early days. We haven't optimized the allocation of actors. We can have hotspots in our execution model, but our simple implementation that we have right now for the 2.0 version does show some pretty good scaling when the queries get a bit sizable, which is the previous example I showed you, hitting 12 rules on average, 1,200 inferred answers, and we see that if we have a single executor that all the actors live on, and it's the only one doing the work, we end up with a 16 millisecond response time on average for an answer, compared to with 8 threads doing 8 executors, each handling some resolvers, it drops down to about 6 milliseconds. This will improve over time as we find better strategies for allocating resolvers onto threads and improve the reuse aspects and optimizations that we can reveal in the actor model. Now, I just wanted to drop in a little tip here because a lot of users do use the reasoning engine to exhaustively query for all possible answers to their query. You can do that. It's completely valid. It's a completely valid way of doing things. You will get a lot faster results if you can somehow estimate approximately how many answers you're going to get ahead of time, or if you only need, say, 10 of them to render your web page or something like that. It can really help your performance to add a limit to your query. And the reason for that is that once the reasoning engine has explored all the answers it finds, to verify that there isn't possibly one more answer hidden over here in the data, it has to search any applicable data that it thinks might contain an answer. So in this particular example, if I were to drop on the limit 1,200, so it does exactly the right number of answers it looks for, it would improve the performance of this entire graph across the board about 30%, which is quite significant. And we have ideas, again, due to the actor model, on how we can reduce this overhead and cost. Now, I think we're getting towards the end of this talk. Yeah, so what do we have? Well, in summary, we've got a new resolution algorithm that's composed of actors, and the actors operate in a computation graph rather than a stack. And this collaboration is a bit similar to TensorFlow, a bit similar to Spark, which do market themselves, I believe, generally as computation graph operational algorithms. And what we also see in the actor model here is that it is natively scalable. The previous diagram I showed you, when we increased the number of executors, all we did was change a parameter, and we got free speed, which is great. And in practice, you could just throw more CPU resources at it. That was showing one query running. If you have many queries running in parallel, and there are only 2 threads handling all of the transactions and all of the actors for all their transactions in parallel, you will find benefits to throwing more CPU resource at the problem, which is something we didn't have the ability to do before. And besides native efficiency gains in the actor model, this is a real benefit. And furthermore, there's nothing nasty we have to deal with like a lock, because all of the implementations of resolvers, when you're working on one of the resolvers, you only have to think single-threaded. Now, as we saw, there's these reuse points in the model where we can naturally find and discover places where work has maybe already been done, and we can reuse it, or we can continue work from other places. This kind of thing was not easy to see before, and now it's almost trivially visible and also quite easy to implement normally. And lastly, this is quite an exciting one, I think. We have a new and accessible vocabulary to discuss reasoning. Before, it was a bit obscure, a bit nebulous, maybe to the community, what the reasoning engine does and how it works. And hopefully through this talk and the new vocabulary we have introduced, we can have more meaningful conversations with you about what you see in your reasoning engine, or maybe you can suggest ideas, and in general have more productive conversations. So all in all, I think this talk has hopefully opened your eyes a bit to what the reasoning engine does and how it works now, also a little bit compared to how it worked before. Maybe you've taken away that actors are really great, which they are, and you want to use it in your project. But regardless of all that, I hope you enjoyed it and learned something about TypeDB. Thank you.